In this example, we want to use the limit definition of the derivative to find the derivative of f of x equals x over x plus 2. Okay, so the first step is to bring up that limit definition of the derivative. The derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. So let's evaluate this thing. So we have the limit as h goes to 0 of f of x plus h. So this means every time I see, so we have x plus h here. So every time I see an x, I'm replacing that x with x plus h. So that gives us x plus h over x plus h plus 2. That's f of x plus h, f of x plus h right there. All right, then we subtract off f of x, so minus f of x. F of x, you just cut and paste. Whatever this is, just goes right down to f of x. All right, so there's f of x. And don't forget to put it all over h in the denominator. All over h. What a mess. But at least it's set up, and it's pretty much algebra from here. But of course, algebra is the most challenging part of calculus. So let's get a common denominator here. We'll call it the least common denominator for these top two expressions here in the numerator. And I'm looking at these two denominators here. So I'm thinking x plus h plus 2 times x plus 2. That's a good denominator there. So let's clean this up a little bit. So we'll multiply the expression on the right here by x plus h plus 2 over x plus h plus 2. And on the left, we'll do x plus 2 over x plus 2. This gives us then the limit as h goes to 0 of x plus h times x plus 2 minus x times x plus h plus 2 all over, and I'm just going to combine the denominators with this h right here, so we have h times x plus 2 times x plus h plus 2. And you may be saying, well, why can we just combine denominators like that? Well, remember how fractions work. If you have a over b all over c, this fraction just bumps down one level, a over bc, essentially. So we can combine with this h down here in the denominator and just make one denominator and save ourselves a step. Okay, so let's clean up that numerator a little bit here. We have the limit as x, let's make that h. H goes to 0. H is the thing going to 0 here. Let's see, x squared, I'm just foiling here, x squared plus 2x plus hx plus 2h minus, okay, so I'm going to make sure I bring this minus through to all these terms, minus x squared minus xh minus 2x. All right, don't forget the denominator. I'm just going to copy the same denominator. H times x plus 2 times x plus h plus 2. Okay, well now we get some cancellation at least. Let's see here. These x squareds cancel. Our 2x's cancel. And our hx's cancel. Look at that. And then what do we have left? Let's just regroup here. So this is the limit as h goes to 0 of, well, look at this. There's 2h over h x plus 2 x plus h plus 2. And here we go. We have finally met our main goal, which is to get this h to cancel. When you're doing these limit problems, you always want to get that h in the denominator to cancel because we're letting h run to 0 and you can't divide by 0. So it's important to get rid of that h in the denominator there, which we finally have. All right, so now we finally have something we can work with. Limit as h goes to 0 of 2 over x plus 2, x plus h plus 2. And now we can very easily essentially just plug in 0 for h, which gives us the final evaluated limit of 2 over x plus 2 squared. And remember what we've computed here, this is f prime of x. Okay, so there's our final answer, the derivative. And then if we wanted to, we could compute something like, f prime of, maybe 1 or something. You can evaluate this derivative once you have it at any point you would like. So what is that? 2 over 3 squared, so 2/9. And that gives us the slope of the tangent line at any point we could possibly want. So any x value, plug it in, it gives the slope of the tangent line at that point. So really, doing the derivative this way is quite powerful. Of course, you don't use the limit definition forever. There are tricks and techniques to evaluate these limits more quickly, but it's nice to get a good foundation with this limit definition of the derivative.